In this video, I plan to discuss Kepler's three laws. Like normal, I'm going to go through some theory, and then I'll go through some work examples. Please read the success criteria I plan to cover in this video. So first, let's talk about the difference between a circular and an elliptical orbit. So most people think of here's the sun and here's the Earth traveling around in a circle. Now, if we assume it's traveling in a circle, we talk about it moving at a constant speed as it goes around, and the sun would be in the exact center. But we could also be talking about the Earth going around the sun in this kind of fashion, where at one point of the year it's closer, and at the other part of the year it's farther away, and it's traveling here in an ellipse. Now, if you want to do an ellipse, I've done this in my class before. Take a piece of string and attach one end here, and then with the other end attach it here. Now we want it to be a little bit longer than the actual distance between those 2 points. So I'm going to stretch it out and put my pen here at the top. Sorry, those are supposed to be straight lines. And I stretch that pen all the way around as I go through. These distances here, so in other words the length of the string, is always going to be the same. And this is how you can actually make an elliptical shape. Whereas if I wanted to do this one, I just put my one end here, fix it, put my pen at this end of the string, and I go around. These places here that I put my pen, we're going to call the focus, two of them being a foci. And what's going to happen, and we're going to talk about this in this video, is if the Earth is traveling in an ellipse, then in fact it's not traveling at a constant speed. We'll get to that in a bit. There are plenty of times when I do want to do a simplification to a circular orbit, like this one. And that's so I can use these two equations that we can find in our data booklet. Now, this one is the universal law of gravitation. G is our constant, which we find in our book. M1, M2, those are just the two different masses, and sometimes you see them as capital M, little m. In this case, it'd be the mass of the star and the mass of the planet. And I also have this equation as well. Now, this is for centripetal acceleration. I can either have its linear speed squared over its radius, its angular velocity or angular frequency squared times the radius, or because it's traveling at a constant speed, we know that the velocity is just going to be the distance around, which would be 2 pi r, and the time it goes around is a period. If I do this substitution in here, I will get 4 pi squared r over t squared. Now, if I want to turn this into a force, because it is this force due to gravity causing my Earth to travel in a circular orbit, well, I just need to use my force. Centripetal would be its mass times its centripetal acceleration, right? Just Newton's second law, F equals ma. So then I'd write m here, and well, let's put it at the end here. Now, which mass is this? This is the mass of the thing undergoing the centripetal acceleration. So in this case, that would be this mass of the planet. I'm just going to put a little blue P here to remind us that it is the planet. So let's start with Kepler's first law. His first law says planets move in elliptical orbits with the sun as the focus. And so whether it be our sun, and this is our Earth, or any star that has a planet circling around it, the sun will be here at one of the two foci. Obviously not at both, but it could be at either one. Kepler actually did this based on empirical measurements. In other words, he didn't have the theory behind it. He just did this by observations, and he came up with these three laws. So the first one saying, no, those planets are not traveling in a circle, they're actually traveling in an ellipse. So let's move on to his second law. A planet covers the same area of space in the same amount of time, no matter where it is in its orbit. So let me draw here. Let's say in the first, let's call it 1 day. It travels this far. What that means is anywhere else in the orbit, this line will cover this much area in the same amount of time. So if I draw another triangle, let's say all the way out to here, to have the same amount of area, I'm going to have to do it like this. Now what I'm trying to draw is that this triangle, if I measured the area of that triangle, it equals this area here. So what's a consequence of that? Well, our planet has gone from here to here in the same amount of time that it went from here to here on this side. That means our planet is going to travel much faster when it's closer to our star than when it's farther away. Sometimes this is also known as the law of areas. And now to Kepler's third law. So earlier I said we had this planet going around, and I'm going to simplify this using a circle. We have the force due to gravity, given here, and because it's traveling in a circle, there must be a centripetal force. Now remember, the centripetal force is a net force, and it has to be caused by something. In this case, the force due to gravity. So I'm going to say the centripetal force is the force due to gravity. Let me put in some information. Mass, remember this is going to be the mass of the planet. I'm just going to put a little p there. And I'm going to use this version of the acceleration. 4 pi squared r over t squared. And that's going to equal big G, mass of the planet, mass of the star, all over r squared. And r then will be the average distance between the planet and the star, or the Earth and the Sun, whatever we're using. So let's take a look here. I've got some things that can cancel out, and I'm going to put all the r's on the left side. So I've got 1 here, and when I move this r squared over, I've got to multiply both sides by r squared. That's going to give me r cubed. And I'm going to move the t squared to this side. And I'm going to put everything else in a bracket right here as a coefficient. That means I'll have big G, mass of the sun or star, and over 4 pi squared. Now remember I said that Kepler did this with observations, empirically. So his third law was actually that the radius cubed is proportional to the period squared. Remember, he didn't have Newton's universal law of gravitation to explain this. He just did it by observations. We now know we can do the equation with this as a coefficient, the universal gravitational constant, the mass of the star or the sun, and 4 pi squared. So let's go through an example. I have here a planet going around in our ellipse. So here must be my star, here's the planet that's going around. It says that the period of the orbit is 100 years. The planet's current position and direction of motion are shown. Let me point out that it is at the closest position to our star, and that's going to be important. It says use one of Kepler's laws to determine the position of the planet in 25 years. Mark this on your diagram. Well, I'm going to be using the second law. Now, due to symmetry, if it takes 100 years to go through, if this is time 0, it's going to be here at time 50. 25, what we need to decide is where is it going to be? And you might just say, oh, it's going to be right here in the center. And unfortunately, you'd be wrong, because that would assume that it's moving at a constant speed. Now, if you remember, we said one of the consequences of the second law is that it travels faster when it's closer to the star than when it's farther away. That means it's going to be able to travel more than halfway in the first 25 years. So anywhere in this range here would be acceptable. Why? Because it was traveling at a faster speed here and a slower speed here. Now remember, the question says mark this on the diagram. Use an X here. Do not draw a range like I have. You have to make a decision because it's asked for a position. For part B, I'm going to say using second law, we know that the planet travels faster when closer to the star. This means the planet will go more than halfway in the first 25 years. And if this question was worth, let's say, 3 marks, I would actually, instead of just saying the planet travels faster when closer to the star, I would include a statement about the law of areas. And then I would put this for our 2nd mark and this for the 3rd. If it's only 2-mark question, then I would answer it as I've given. Example 2. We have this same planet here that had the orbit of 100 years. But now we have a second planet, and its radius is 1.4 times the radius of the original planet. What is the new orbital period? Well, let's use the 3rd law. Remember we said that r cubed is proportional to t squared. And if I just want to put that as an equation, I'm going to say r cubed equals some constant, don't care what it is right now, t squared. Now, I've got 2 planets, and this is going to have to be true. And since we are around the same star, it would have the same constant value here. So let me just make a ratio, because that's what we're going to do between these 2 planets. So if I go r of planet P cubed equals k, the period of planet P squared, and I'm going to just divide it by the equation r, and let's say n is for new. It's going to have the same k, it's going to have a different period. I'm going to do that because we know this is an equal sign and this equals to each other, so when I divide it, I really should have the same value on each side. Now notice I'm going to be able to cancel that with my k. And let me rewrite that up here. I'm going to r of the planet cubed, and the new one has 0.4 times r of the planet all cubed. Notice that 0.4 is inside the bracket that will be cubed, and I need the period of the planet, which we know is 100 years, squared, and the new one is what we're looking for. Now, again, these r cubed are going to cancel, and if I move this around, I have the new period. We come up here, this will be 0.4 cubed times 100 squared, and I'm going to do the square root here. I'm going to pick a handy dandy calculator, and I get 25.3 years. So, I hope that's helped. Please read the success criteria one more time, and hopefully you can say yes to each of these.